Welcome in, everyone. In this video, I'm going to go over extreme values. First, I'm going to go over what they are as a definition and graphically, and then I'm going to go over how you can find them. And that will include how you can find them on both closed and open intervals. Let's get into it. Before I get into the calculus for this video, I want to take a college algebra trip down memory lane. And just to hopefully jog your memory in that you have analyzed graphs of functions before. So as you take a look at this graph here, you can notice there are some numbers being pretty well specified on the x-axis. And the first thing I want to bring back to the front of your memory is that functions can decrease and increase along the way. And so I have these red values here already listed out to help us with that. So as we move from left to right, we can see that the function is decreasing from negative infinity to negative 5. Then at negative 5, the function stops decreasing and starts increasing all the way to 0. So let's do that, increasing from negative 5 to 0. And then it starts decreasing again, so we'll union another interval here from 0 to 4. And then again it starts increasing again at 4 all the way off to infinity. The other part here, the yellow numbers are where all of the x-intercepts for this function are. Now with the yellow numbers, what they help or how they help organize this graph is either to be a positive piece of the graph, aka above the x-axis, or a negative piece of the graph, aka below the x-axis. And we can divide them up like that too. So we can say f of x, otherwise known as the y values, are positive, bigger than 0, for the following intervals. From negative infinity to negative 9, again we're moving left to right, it's below the x-axis here, but here between negative 1 and positive 1 it's above, and here from 7 off to the right, off to infinity, it's also above. And we can do the same thing for less than 0 or negative function values. It'd be from negative 9 to negative 1 and 1 to 7. Now one last thing we can do here is we can notice that there are minimum values, aka the lowest point on the graph, and a maximum value, aka the highest point on a graph, for this function. Now a very quick distinction here, this minimum value is lower than this minimum value, and that will be important in just a few moments. So what are extreme values? Extreme values are the maximums and minimums of function values. Function values are the y values, so we're looking for the maximum y value or the minimum y value. And basically it boils down to the x values that make the derivative equal 0 or make the derivative undefined. Now I want to stop here and just point out that yes, now we're starting to work our way up into calculus. And what we're going to do is we're going to use the derivative to describe characteristics of the original function. So we're still telling where the original function has maxes and mins, but we're using the derivative to do it. So we're using calculus to explain college algebra ideas. I think it's pretty cool. Anyway, with extreme values, there are two types, which I will go over on the next slide. So what really are extreme values? Okay, so glad you asked. We are going to let f be a function with the domain D, and we'll let c be a value of D. So this is some specific x value. If we let these things be true, then f has an absolute maximum at c if for all other values of x on the entire domain, the y values are less than the f of c y value. And the same thing happens for an absolute minimum. All of the other y values are bigger than or equal to that y value when x is c. I think that makes sense. The smallest y value or the biggest y value for everything else in the domain. Now down here I have two other ones. We have relative max and relative min, and I ran out of space. But these look very similar, but they don't have to be the biggest out of all the y values. It can just be the biggest of the y values nearby. We would say in a small neighborhood. And in order to help you get a better understanding of this, we're going to move to the next slide. On this slide, you can see that we have a function that's graphed, and the function is just defined on the interval from a to b. So we're not going to concentrate on anything outside of this interval. And what I'm going to do is I'm going to first find the absolute max and the absolute min for this function. So really, when we're looking for the absolute max or min, we're just quite literally trying to find the highest point on the graph. That's it right there. So this would be considered the absolute max. So I'll go ahead and abbreviate abs max. And then the absolute min is the absolutely lowest point on the graph, absolute min. There's no point on the graph lower than this one and no point on the graph higher than that one. Now, there are some other maxes and mins within this graph. That's what we're going to call relative max and relative min. So here, since you can tell there's a minimum here, we're only looking in like a small interval for that minimum. It's definitely not the minimum of the entire graph because we found it over here, but it is a minimum because there's a little dip. It stops decreasing and starts increasing. So there's a minimum there. And likewise, there's a minimum or a maximum here. But again, it's not the absolutely tallest point or highest point on the graph, just within a little area around it or a little interval around it. So we would call these relative mins and a relative max. But even in addition to that, we can say the same thing here around the endpoints. This endpoint on the left is the tallest point. It's the highest point in a small interval around it. So this is even here a relative max. In the same similar idea over here, we have a relative minimum because in a small interval around this point, that is the lowest point. So that is the difference between absolute and relative. You can have only one absolute max and one absolute min value, but you can have multiple relative maxes and mins. So how do you actually find the extrema? Well, first we're going to start with the closed interval, and I'm going to point out that the word extrema is the math word we use to call extreme values. So the first thing you want to do when you're looking for extrema on a closed interval is find all the critical values, and this is where the calculus happens. From there, we will take the critical values and the endpoints, and we will evaluate the function at all critical values and endpoints. Then we will pick the largest and smallest values from step 2, and these will be absolute extrema. And just for reference, I mentioned critical values here. A critical value C is a value that makes the derivative equal to 0 or makes the derivative undefined. Finally, an example. What we're going to do is look at this function on this closed interval and find the extrema. So the first thing we have to do is we have to find all critical points, or all critical values. So what we're going to do is take the derivative of what we're given. So f prime of x will equal 1 over 3 x to the 2/3 power. Just based on the power rule, remember the cube root is the same as a 1/3 power. Bring the 1/3 power, subtract 1, push it down. So there is the function. Now in order to find the critical values, what we are going to have to do is, since critical values are the x values that make the derivative equal to 0, we can set this equal to 0 and try solving for x. So x to the 2/3 power equals 0. And if we're going to try to do this, we really are just going to multiply both sides by this value right here, and we'll just end up with 1 equals 0. It's not going to work out. We're not going to get any solutions here. But a critical value is defined as the values that make the derivative equal to 0, or where the derivative is undefined. And since we have a denominator here with a variable in it, we can set the denominator equal to 0 and solve for x as well to find where the function, or where the derivative, is undefined. So we can divide both sides by 3. We can raise both sides to the 3/2 power to solve for x and just get x equals 0. So this is where f prime of x is undefined at x equals 0. And that is the only critical value that we have. So what do we do from here? We move on to step 2 from the process, which said to take all of the critical values and the endpoints of the interval and evaluate the original function at those values. So we're going to find f of 0, f of -8, and f of 1. So f of 0, the cube root of 0 is 0, f of -8, the cube root of -8 is -2, and the cube root of 1 is 1. And it is literally picking out the smallest and largest number in this list right here. So this is where the absolute min is, and this is where the absolute max is. And how could you write that out a little more clearly? Like this. F has an absolute maximum value of 1 from here at x equals 1 from here, and an absolute minimum value of -2 from here at x equals 8 from here. Let's take a look at another example. All right, new function, new interval. Let's get to finding the extrema. And in fact, again, this will be the absolute extrema because we are doing it on a closed interval. All right, so the first thing we have to do is find the critical values, which will require us finding the derivative of this function. And it just requires a little bit of a power rule here, 3x squared plus 2x minus 8. Now, the difference between this function and the previous one is that there is no denominator here. So we don't have to set any denominator equal to 0 to find out where the derivative is undefined. What we'll do instead is we will just take the derivative as it is, set it equal to 0, and solve for x. In this case, we can actually solve for x here. And again, it doesn't matter. You see it's quadratic. You can use factoring if it factors. You can use the quadratic formula if you're comfortable with that. But this will factor to 3x minus 4 times x plus 2, and that still equals 0. So our critical values after you do some quick solving will be 4/3 and -2. Now I'm going to stop right here because I wasn't able to do this in the last example. Take a look at the critical values, 4/3 and -2. Now look at the interval of which we are interested. Is 4/3 in this interval? Is 4/3 between 0 and 3? Yep. Is -2 between 0 and 3? No. So we will not use this this second number because it's not in 0, 3. So don't use that because it's not in 0, 3. And since it's not in that interval, why would we bother with it? All right, so we have our critical value, we have our endpoints. So let's evaluate the function at the critical values that we are going to use and the endpoints. So here we go with that. We have f of 4/3 equals -41 over 27. There was some pretty good simplification going on in the background here. F of 0 is 5 and f of 3 is 17. So you can tell that this will be the smallest value, this will be the largest value, and so I'm just going to say it this time. The absolute min of f is -41 over 27 at x equals 4/3, and the absolute max of f is 17 at x equals 3. Now, another thing I want to point out before I move on to any more examples or theory. In this entire example, there is one calculus step, and that is finding the derivative. Everything else that you're learning has come from a previous course. How do you solve a quadratic equation? You learn that before you get to a calculus course. How do you evaluate a function and simplify? You learn that before you get to a calculus course. So calculus 1, in my best opinion, is when students find out whether or not they truly understand the algebra they learned before. And of course, you know I can't make a video without throwing some trig in there, so let's do one more on a closed interval for a trig function. I'm going to make it relatively simple. F of theta equals sine of theta on this interval. So again, the first step, the only calculus step that you'll see in this whole example, take the derivative with respect to theta, we'll get cosine of theta. And this is where solving trig functions comes into play. So we have to take the derivative, cosine of theta equals 0, and we have to list out all of the places where cosine of theta equals 0, but we're only wanting to focus within this interval. So remembering back to your trig, you should remember that theta here will equal odd multiples of pi over 2, aka 1 pi over 2 or 3 pi over 2, etc., etc., etc. So let's write out what we have here. We have pi over 2, we have 3 pi over 2, and that's it for the positive versions, because if we go to 5 pi over 2, we are no longer in this interval. Next, we've got to come up with all of the negative versions. So the only one, and yes, I mean one, the only one that we'll have to deal with here is negative pi over 2. And you might be asking, well, why not negative 3 pi over 2? That is an odd multiple of pi over 2. And we do not include it in the list of critical values because it is the endpoint. And that's the only reason. So we have our critical values, we have our endpoints, and for completeness sake, I'm going to say we don't have a denominator to worry about. So we don't need to set the denominator equal to 0 to find out where the derivative is undefined. We would say the derivative is defined everywhere. All right, so let's go ahead and evaluate the original function at all of our critical values and endpoints. So here are all of the evaluations of the critical values and endpoints in the, again, original function. We're using the derivative to find the maxes and mins for the original function. Now, you might notice something strange about these is that there are 2 instances of the maximum value and even 2 instances of the minimum value. Which one is the absolute max and which one is the absolute min? Well, it turns out there is an absolute max of 1 for function f at x equals pi over 2 and x equals negative 3 pi over 2. Like this down here. It is possible to have the same maximum value show up twice. As you're seeing, think about how the sine graph looks when you graph it out. It's just this wavy function. But again, we can say this something similar about the minimum values. That f has an absolute minimum value of negative 1 at both of these x values. So while we can only have a single value for a maximum and a single value for an absolute minimum, it can happen in multiple places, and if both of those places or all of those places are happening within the interval, you should list those out. And without missing a beat, we're just going to jump into how to find extrema on open intervals. So I think the biggest difference right off the bat is you can see we are not given an interval to have endpoints. The only thing that we will have for this function are the critical values we find to find whether or not we have a max or a min. The other big difference is because we don't have this interval, we can no longer say that it will be an absolute maximum or an absolute minimum. Anytime you're finding extrema on an open interval, we just default to saying relative maximum or relative minimum. But the process is still the same. So let's take a look at this function, f of x equals x to the 2/3 power times x plus 2. Now, with this, you can certainly, if you want to, use the product rule. I'm going to take a slightly easier route. Since this is relatively to distribute, I am going to do this first and get this. X to the 5/3 power plus 2x to the 2/3 power. So now instead of doing the product rule, I can go ahead and do the power rule. So the derivative will look like this. F prime of x, just by power rule, will be 5/3 x to the 2/3 power plus 4/3 with an x to the 1/3 power in the denominator. Now this looks like something that's a lot more fun to solve. Okay, before I even get into solving this, I want to notice that I have an x in the denominator. So when I set this denominator equal to 0, I will find that x equals 0. When you solve it, x equals 0 is where f prime of x is undefined. So there's one critical value right away. The other fun part to this is that now we have this equation to solve for x. Again, this was the only calculus step. Everything else in this example is going to be something you learned in a previous math course. So how do you solve this? Well, first I would like to get rid of the denominators, so I can see we're going to multiply each term by 3 and an x to the 1/3 power. And that leaves us with 5x plus 4 equals 0. And again, you can see that when you come back and multiply each term by 3x to the 1/3 power, the right side of the equation is clearly 0. The 3 will reduce here, leaving you with x to the 1/3 times x to the 2/3, which is x. And then everything will reduce here, leaving you with the 4. And then you can just solve this for x, and that gives you x equals -4/5. So again, as I mentioned, we now have all the critical values that we can find where the function or the derivative is undefined and where the derivative equals 0. And those are the only values we get. We have no endpoints to substitute back into the original function. So let's substitute 0 and -4/5 back into the original function and see what we get. Here you go. These hilariously fun values. This one was hilariously easy, and this one was hilariously difficult to compute or to look at. Anyway, when you substitute 0 in for x here, it zeroes out everything, so f of 0 is 0. When you substitute -4/5 in here, you can square 4/5 to get the 16/25. And then the 1/3 power turns into the cube root. You can leave it as a 1/3 power if you like. But then the -4/5 plus 2 is where the 6/5 come from. All right, now for the statement. And it bears writing out both statements this time because, as I mentioned at the beginning, when we don't have a closed interval, we are finding relative minimums and relative maximums. So f has a relative min of 0 at x equals 0, and f has a relative max of 6/5 times the cube root of 16/25 at x equals -4/5. All right, last example, let's get into it. This function is different because it's piecewise. I do want to point out and maybe bring back something that you've already learned, in that this function is continuous at x equals 0. You can tell just by substituting 0, that's where the functions break. Substitute 0 in for all the x's, and they will both equal 3. So it's continuous. Let's go ahead and get into this. Let's see here. We can take the derivative f prime of x equals the top function will be -1. For x less than 0, the bottom function will be 2 minus 2x for x greater than or equal to 0. And something interesting happens here. If we take a look of the graph of this derivative, the top portion is -1, which is just a horizontal line as long as x is less than 0, so the open circle here to the left. And then when x is greater than or equal to 0, this is a linear function that starts at +2 on the y-axis, the y-intercept, and then a slope of -2. Now there's a discontinuity here at x equals 0, which means there is a critical value at x equals 0 because the derivative does not exist at x equals 0 because of this discontinuity. So we find a point where the derivative isn't continuous, which means the original function isn't differentiable, which means the derivative is undefined at that point. So f prime of x is undefined at x equals 0. But from there, we can go ahead and check where the critical values are for this particular function down here. There are no x's to solve for, so we're not going to get any critical values from the top piece. But the bottom piece has an x, so we can set it equal to 0 and solve for x. And we can say that x will end up equaling 1. So f prime of x equals 0 at x equals 1. So we have two critical values to look at. And let's substitute these back into the original function at in the appropriate piece of the original function, so we can find maxes and mins. So here I have substituted 0 into the appropriate part of the function and 1 into the appropriate part of the function and got these values. So yes, 3 is the relative, min at x equals 0, and 4 is the relative max at x equals 1. And another big concept within calculus is you're not supposed to use graphs to prove what is going on. However, here is a small version of the graph of the original function up here, and you can tell that right here there is a minimum value. It bottoms out, and right here at x equals 1 is the maximum value as it tops out. So it still works, and this brings in the idea of differentiability, essentially making sure the derivative is also continuous at that particular x value. Since it wasn't, that means the derivative was undefined at that x value. I hope this video helped you out. Good luck.